Hello, Mr. Ryan, right?
Yeah.
We're given two arrays of integers, and we want to find the smallest, the minimum common value. So put it other words, we want to find the smallest value if it is appearing in both arrays. Here, in this case, 0. Okay. What's your source? And if we don't find such number,
We return -1.
we'll return -1. Yes. If we can't find any, return -1. Okay. Not found. Any idea?
So we sort both of them and then just work along.
Good job, sort, right? Okay, so I didn't tell you if it's sorted, okay? So we sort it, okay? But if it's sorted, we don't need to sort it. So how do we work through? These two are already sorted, right?
We check.
How do we work through?
So we start both of them like a 2-pointer thing, and if like so the B one is smaller, so we just move to the right. Now the A one is smaller than the B one, so we move to the right. It's still smaller and
Which one is small? Now move this, yeah?
and it's still smaller than 0, so we move, and then both of them are same.
Okay, and then if there's no zeros here, if I put 1, what happens?
Then the B
Yeah?
one moves to 5, 1 moves to 2, 2 moves to 100, 5 moves to 1,000, and then 100 moves to nothing.
And then when it's nothing, we return -1. That's good job. Okay, that's very good. We are given two sorted array. Let's say we're given two sorted array already, okay? So if we want to sort them, if this is the length is n, then the time complexity is NLogM, right? Okay. So if we are given already two sorted array, and if the length is n, the length is m, what's the time complexity? How many steps maximum together?
2 pointers.
Yeah, I know. What's the time complexity? N, m. What should I put here?
Plus.
Plus, yes, because at most you are working n plus m, right? Okay, so this is the time complexity. If the arrays are not sorted, we can use the set, right? So we just convert it to set. So set A, right? Converting these to set n, set B, n, right? Intersection, right? Look, remember, this is A, this is B, this is A, this is B. A and B is here, right? The common part. And then we need to sort it, right? The common part we sort it. Sort it, then we convert it to a list. And then return the first one if there is any, right? If there is any. If not, we return -1. So we set A and set B. If set N and set B, we put it as C. C equals to N and set B. And then if C, we sort it and return the first one. The time complexity for this one is, look, if there are n elements, m elements, right? And if they are both the same, right? If both arrays are the same, so n, let's say n, the time complexity is NLogM. Okay? If A and B are exactly the same, so the intersection is itself, right? And then we need to sort it. Is NLogM, and then get the first one if there's any. This is the case that when the two arrays are not sorted. First solution is NLogM, right? NLogM, which is within the set. Space complexity is O(n). The second approach is O(n plus m), and the space complexity is 101, right? Because we don't use any other space. Before we go into the third approach, let's just quickly implement the second approach, which is the 2-pointer. The length of A equals the length of A. The length of B equals the length of B. And then the left equals right equals 0, right? 2-pointer, left and right. While left smaller than LA and right smaller than LB, right? When we haven't reached the end. Then if AL equal BR, then we return AL, right? It's the same, we return this. Otherwise, if, right? If. This is else if. If AL smaller than BR, what should we do here? Else, what should we do here? If AL smaller than BR,
+1.
AL plus equal 1. Else
B plus.
R plus equal 1, right? 2-pointer. And then if we don't find anything after the loop, when we reach the end, the conditions do not meet anymore, then we return -1 here. return minus 1. Okay, so this is the 2-pointer thing. The third approach is that, look, because two arrays are already sorted, we can binary search, right? So we go through this each number, minus 3. Then we binary search this number in this sorted array, right? For I in A. Right? We go through each number and then you tell me the time complexity. And then we need to bisect, right? Bisect left. Remember the bisect left and bisect right. The binary search.
Yeah.
Okay, so look, bisect left. Look, 0, 1, 2, 2, 3. Okay? Look, this is already sorted.
I know.
Then if we bisect, look, every time I talk about bisect left, I will talk about this example. Bisect left, this array is A, okay? A, let's find 2. Find 2, then you will return this position. But if we bisect right, A2, you will return this position, okay? This is the difference. So it basically returns that this position where to put the new 2, you still sorted, right? Bisect left and right. So we find it. If the element is not in the array, then it returns the position where we can put that element in, right? So how do we use the bisect left to check if the element is in the sorted array? We can do this, right? X equals bisect left, bisect, B-I-S-E-T, left. B, we want to find element I in array sorted B, right? Then if X is smaller than the length of B, and also we come back to check if B X equal I, right? Look, this is to check if we found the element I in the array B. Then if it is, then return I, otherwise return minus 1. So we are going through the numbers in array A, and we check if the numbers can be found in the second array. And then because the second array is sorted, right? So we can use the binary search. If it's not sorted, the worst case, how do we check it? We just go through the first number, second number, third number, right? And the time complexity for that one is what? On times m, right? The Bruteforce, on times m. Okay? This is another approach, on times m. On times m. Right? Going through the first number, array in the first number, and check if the second array has it, right? On times m. But the thing is that this m, this second array is sorted, so we can use the binary search. The linear search is OM, and when we binary search it is O log M, right? We bring down the complexity to O log M. So the time complexity for this one is O n times log M, right? So because this is a sorted array. So how do we find such element in the sorted array? We use the bisect left, right? Bisect left. So remember the numbers here, 0 to 100, cut in the middle, 50, cut in the middle, 25, right? 12. 6. Okay, we find the insert position, and if it's within the range, right? Because it possibly will be here, right? The return position will be here. We want it to be the insert position will be here, right? Here, and also if the insert position, the value, we come back to check if the value equals I, then it means that the number in the array, right? So look at 2. It returns this position, and we come back to check A2 equals 2. Then okay, so we have 2 here. How about if we want to find 2.5? 2.5, it will return the position here, right? Here. But when we come back to check it, there is no 2.5 in this array, so it's not there, right? Makes sense. Okay, so look, there are 2 arrays. We can go through the second array, binary search it in the first array. Which one is better? 2 arrays. I didn't say it's the same length, right? Okay? This approach, I was just saying binary search. We go through the numbers in the first array, binary search the second one. Or we can go through the arrays in the second one, binary search the number in the first one. Which one is better? I mean, so basically, look, this is A, this is B. The first approach is go through the numbers in the first one and check if the number appears there. And the second approach is that I go through the number in the second one and check if the numbers appear in the first one using the binary search. If it's a Bruteforce, O n times m equals O m times n, right? Because n times m equals n times m, right? This is simple, right? But with the binary search, it's different, right? Binary search is what? N times log m and n times log n, right? Okay, so which one is better?
You said that that it doesn't, you can't, they're not always like the same size.
Yeah, so we need to check if n is so bigger than m, right? If n is this is big, we want to make it binary search, right? Am I right? If n is a million, okay? So it's better I put it log n, right? Because look, remember the log n thing is this, right? So it brings down the complexity. So if you want to put the n is so big, so you might want to consider this one, put it there to bring down the complexity, right? So when n is bigger than m, we choose the second one. When n is smaller than m is bigger, then we choose the first one. Make sense? Does it make sense? Yes.
Yeah.
Okay. First approach, Bruteforce. It's actually the Bruteforce n times m. Eh? We go through each number and then we just Bruteforce to check if it appears on the second one. The second approach, using the hash set, right? We're using the hash set. So we turn this A into a set, turn this B into the set. We use the intersection n, right? And then when we have the intersection, we still have to sort it. In the worst case, A and B is the same. Then all the elements are the same. So we convert it to the set is O times n plus, and we need to do the sorting, right? Do the sorting is O n log n, right? Okay, and the space complexity obviously O n, okay? Okay, the second approach. The third approach, by the way, very well done, is 2-pointer thing. This is actually quite similar and merging two sorted array, remember? We merge it, right? Two array is sorted, 0, 2, 4, 6, 10. Another array, 1, 3, 5, 7, 9. Yeah? How do we merge it? Right? 2-pointer, the same idea, right? Smaller, use this one, move it. Smaller, move this one, use it, yeah? Okay? This is actually exactly the same, except that we are looking for the common element instead of merging them together. The time complexity, O(n) plus m. The space complexity, O1, right? And the fourth approach is binary search. So because both arrays are sorted, we can go through one array and then binary search in another array. So the time complexity is this one, right? O(n) times O. And which one is better? Look, is this one better than O(n) plus m? Which one is better? O(n) times log m or O(n) plus m? Which one is bigger? Which one is smaller? Okay, now I'm saying O(n) plus m or n times log m. Which one is smaller? If n is a million, then they're going through 2 million times. And here is a million times, yeah, this is bigger than 2, right? So this is better. 2 linear scan is better than this one, okay? Yeah? Because log a million is obviously bigger than 2. Okay? And then this is just 2. Okay, so Eric, your approach is the optimum, is the best, okay? Because it's just 2 linear scan. And this one, the problem of this one is that you have to go through each number, and then for each number you have to binary search in the second array, in the other array, so it takes more time. Am I right? Yeah?
Yeah.
The problem we want to solve is we have two arrays with numbers in them, and we want to find the most smallest number that appears in both of them. If there isn't any, we return -1. So one approach is you scan you do 2-pointer thing, one in A, one in B, or whatever you can call it, right, left, and M, and so if one is smaller than the other, then we just move it, and then if one of them is bigger than the other, we just move the smaller one, and then it goes on until you reach the end, or you find a matching pair.
Yeah, well done. Good job.
And 2-pointer.
Yeah, 2-pointer. Okay, and then Bruteforce, yeah, obviously, and binary search. Okay. Okay, and then using a set intersection of two sets. Okay. Bye bye.
Bye.
Bye.